So next item in this course on modeling is to talk about what is meant by system and the state of a system. So system is the first one we are going to define. It is a part of reality that can be separated from the rest by a discernible boundary. So for example, if you look at this pen that I am holding in my hand, you could say, okay, it's a part of reality which I can separate from the rest. I know there's something that is part of the pen and there's something that's not part of the pen. I have some decision ability to decide which one is inside, which one is outside. That's what we mean by a system. If you're not able to decide which one is outside, which one is inside, then you have a difficult time figuring out what is meant by system. The part that's outside the system is called as environment or surroundings. So you will see that when you take a thermodynamics class, people talk about systems and surroundings and things like that. And that's the starting point. The next idea is state of a system. So we cannot deal with directly with reality. It is very, very confusing and also extremely contradictory in the way in which we use our language and things like that. So what we have to do is systematically convert it into quantifiable entities before we move on, because then we can use the tools of mathematics and the tools of mathematical reasoning. So the first thing is you have to decide what kind of attributes of the system we are interested in. So if you look at this system, I may be able to say, look, I'm very much interested in what's the length of, how big is the pen, what is the color, what's the how much lead there is in it, so to figure out how much use it has, whether it has a clip or not, all these kinds of things, whether it has an eraser or not, all of these things are attributes. And you have to have a measurable way of denoting the attributes. And the measure could be finite or infinite, continuous or discrete. For example, if I want to say what color it is, I may use like wavelength of light reflected or some such measure that will allow me to talk about color. If I want to say whether it has a clip or not, that's a binary value. So I can say 0 means no, 1 means yes. And then I can have many systems, for example, may have only class attributes, and I may have to do some kind of binary definition for all of that. Okay. So in fact, I may be interested, and this is one of the things that we are interested in mechanical systems, is position and orientation relative to a fixed reference, color, maybe how hot it is, all these kind of things. So the state of a system is not a property of the system. It is the property of our representation of the system. This is our cartoon. So the list of states is like eyes and mouth. That is, I have eliminated all the other things and I have converted it into a cartoon by the time I define a state. So it is a characteristic of the cartoon, not of the real system. The real system may have uncountably infinite number of attributes, many of which we don't even know, or we may not even be able to know. So we are not representing reality. We are representing a cartoon of reality. And a state is the first step in the cartoon. So this is actually what you have to decide, and how many different attributes you list will tell you how complicated the state is going to be. By the way, it is possible for the same system to be represented by different sets of states depending upon your interest. So if you think about a box of gas, I can say, look, a box of gas is defined by, state of the gas is defined by volume of the box, temperature of the box, pressure. That's classical thermodynamics, right? Or you could say position and momentum of each molecule in the box. That's the micro level. Or you can go and you say not only position, momentum, types of individual molecules, but also internal quantum state of the molecules. Right? The question is, you cannot say what are the state variables. You have to say what is your purpose. And then decide what are the attributes that you are interested in. if I am primarily interested in how the molecules flow, then I may not need to know all this micro level and nano level information. But if I'm interested in chemical reactions, maybe I may be interested in type of individual molecules. If I'm really interested in some other property, like if I am very much interested in seeing whether I can make a gas laser, then I perhaps may have to include something about the quantum state of the molecules. Right? So the same box of gas may have different representations depending upon different ideas on when it will work. Okay, so you have to always keep in mind that ultimately everything depends upon purpose. So now we come to talk about what is meant by state variable and state space. State variable means a scalar, vector or tensorial quantity. Tensor means matrix at this point. That's all you have to know. So it could be a scalar, a column vector, a matrix, which you can write as a bigger column vector. So maybe you can think of everything as a column vector of size 1, size 2, size 3, size 4, so just think of it, everything as a column vector of a particular size. Okay, and it could be discrete or continuous. What I mean by that is it may be able to take only discrete number of values, or it can take any value between some limits, or it can take any value between minus infinity and plus infinity. Okay, and the idea is it is used to quantify the state. So now you can see gradually we went from system, which is reality, to attributes, which is our initial cartoon, and now we are looking at parameters, which is our state variables. Now we have converted it from reality to a mathematical abstraction, right? So the state variables are used to quantify the state. The same state may have different related state variable representations. For example, if you look at color, it may be represented either by frequency or wavelength. They are related, but they are two different things. Same way, particle, you may think, okay, position and momentum or position and velocity or something like that is what represents the particle, and they are different. They have same amount of information but in different ways. So your choice of state variable actually tells you how you are going to quantify this thing. So for example, if you think about hotness, classic thing is centigrade or Fahrenheit or absolute temperature, Kelvin. All of them are related but different ways of quantification. A state space is a graphical representation of the state of the system, which means it represents it in a coordinate system with each state variable along one axis. So for example, if you have a gas and you decide to do it as a macro level, and you have volume, temperature, pressure. So you have three state variables, and so it will be a dot in a three-dimensional space. One axis being temperature, one axis being volume, another axis being pressure. Right? And typically, more detailed the space, the state space, the higher the dimension of the state space. So, for example, if you think of a gas as being made up of particles, the position momentum of each particle is one element of a state space. So if you have Avogadro number of particles 6.023 times 10 to the 23, your state space will have dimensions 6.023 times 10 to the 23 times 6, because each particle has 6 attributes, 3 position, 3 velocity. You can see the more detailed, the price you pay is dimensionality. And this is bad news, because high dimensions create lots of problems. So again, we call upon Occam's razor to decide upon what's a suitable state space. You have to dramatically reduce the dimensionality of the state space in order to get something that's meaningful. And that's where a combination of intuition, history, your own ideas on what happens, and all of these things come in, so that you can reduce the dimensionality of the state space. So process is a sequence of states, time sequence of states. So if you have a state space, so let's say temperature, volume, pressure, a process is a curve which tells you at each time instant there's a different value of temperature, pressure and volume, right? So our central task is try and predict it given some external conditions. How will it go? It turns out that this is not as simple as it looks because of the fact that we have external knobs and controls. Okay, so we may only know partial information about the system and surroundings, so we may have to make some guess on how it will respond, and that's part